that's fine. Good morning, everyone. Welcome to day 2 of CI Days number 2. We're in for another real spectacular talk today. It's disappointing that we don't have more people here taking advantage of it. I don't know, we've had for some reason pretty high attrition versus the people that registered. We had over 170 people registered for this session, but maybe the weather or something, or final exams. So our talk today will be by John Delaney, and you can look in the website and see his bio. What I'd like to point out as kind of a theme that I've been trying to illustrate with some of the keynotes here is that there are people that are preeminent members of their scientific field and their discipline, and certainly John is held in high regard within his oceanography community, but for various reasons have chosen to step forward and provide the difficult leadership, the professionally altruistic leadership of organizing an initiative within a field to help transform it. And in my opening remarks yesterday, I mentioned something that's often overlooked is that part of the cyber opportunity space is the incredible development of sensors, sensor arrays, and all types of new types of observatories. At NSF, there are funds that support individual research, there are funds that support team efforts, there are funds that support educational initiatives, and there are also special accounts, special funds that support the creation of large-scale instrumentation or research environments, which you would come to mind things like telescopes and so forth for the astronomy community. But in the last decade, there have been enormous growth in observatories, often physically distributed observatories in all types of fields, in environmental areas and the geosciences and oceanography and so forth. And you'll be hearing about one of those examples. So we had yesterday Gerhard Klimek, who didn't talk about the fact that he runs a huge research project with 25 people on the fundamentals of nanoscience, but in addition to that is providing this leadership for this new modality of distributed research and learning. We have John today who's doing similar things within the oceanography community. For that matter, we have our own Brian Athey sitting here that's doing it here in the bioinformatics area. And I just point this out that the key ingredient to innovating in cyber infrastructure that actually transforms the nature of research and learning in new positive ways, that gives us the platform to tackle these grand challenge problems of society, ultimately comes down to leadership. And you can take that as a challenge, if you like, to see if you could place your role in that leadership to benefit the collective. So with that, I'd like to introduce John Delaney from the University of Washington. And as I said, I have not heard the exact talk that John's given. He's tailored it to this day, but I have heard from others that this will be a very interesting experience for you. Welcome, John.
Thank you. Well, it's kind of exciting to come to such a distinguished place. I almost feel a little bit at home because there are a lot of similarities between the University of Washington and the University of Michigan in terms of breadth of scientific and technological engineering inquiry into the world around us, and support from federal funds and things of that sort. So I'm really pleased to have this opportunity, and I thank you, Dan, for the invitation. Also, looking forward to dialogues. I will, of course, as as is expected when you're giving a keynote, I'll talk a lot in the beginning, but what I would really enjoy would be dialogue, either associated with this talk or follow-on dialogue, because there's a great deal of excitement about where we're going at the planetary level in terms of studying the oceans. We're starting necessarily in small ways compared to what is necessary in the long run. And I see that the average age in the audience here is somewhere between 30 and 40, so that's very promising as well. I'm really delighted to see the youthful character of this audience. It's a bit of a bold thing I consider myself, I started mapping limestones in the Shenandoah Valley and working for a mining company about 45 years ago. So my initial image of myself was I'm a simple country geologist just trying to make a living. And I've evolved through living in the Galapagos Islands for 6 months down inside the active volcanoes, to diving to the seafloor many, many tens of times in the submarine Alvin, to developing not an affection but a total passion for submarine hydrothermal systems and underwater volcanoes. So that if there's a central love to my life, it's underwater volcanoes. But in the last 15 to 20 years, it's become clear that no matter what it is you want to study in the ocean basins, our current capabilities, excellent as they have been to get us to where we are not adequate for us to move to the next stages of deep and full understanding at the level of any number of ecological systems. And it is ecological systems, if you want to come down to it. It's the ecology, ecosystems, that really is the great challenge because of the complexity of those systems. And the global ocean, and I will hammer this and hammer this and hammer this today until you can actually kick back at me if you like, it would be wonderful, that the central supporting system on the planet is the ocean. The life support system for the entire planet is the ocean. As goes the ocean, so goes life on the continents. Most people in the continents, and certainly those who are, dare I say, unfortunate enough to live at mid-continent as opposed to on the coastline, tend not to think about the ocean every day. I mean, I can imagine some of you don't even wake up first thing in the morning and think, God, I wonder how the ocean's doing. Perhaps that'll change, perhaps not, but I'm sure as hell going to try to bring that about it. And I will try to make the case not just with humor and sort of offbeat wit, but I will try to actually make the case that the ocean does play critical roles and that the ocean is very, very difficult for us to understand. So let's start with 4 points. In the event that you didn't get enough sleep last night and you do need to take a quick nap, if you write these points down, or in fact I think there's going to be a video available to you. So this is the essence of the talk right here. That the oceans are essential to life on the continents, and I will make that case. That the oceans are very, very complex, I mean more complex than we can imagine right now, and they are changing very rapidly. And they are changing unpredictably. Therein lies the issue. Because so many of the ecosystem services that we take for granted from the oceans are not appropriate for us to take for granted. Sophisticated models that have the potential to predict forward paths, changes in the ocean, are probably far, far along in terms of just that, their sophistication. But they're not very far along in terms of long-range or even short-range prediction. And so the key to shifting some of these very, very elegant models into having the capacity to sort of look around the corner into the future is to feed them data. And I mean feed them a lot of data of a lot of different types almost continuously. And perhaps 2, 3, 4 decades from now, we will have models that can indeed anticipate, quote, changes that will take place, whether it has to do with the restless Earth itself, the solid Earth, or whether it has to do with the ocean itself, or the ocean atmosphere system, or the ocean atmosphere Earth system. And we're not there now for sure. And the novel approaches that I'd like to talk with you about, combined with others that I will probably not talk very much about, can transform the perceptions that the whole society, and I mean the global society, have of the ocean itself and therefore the Earth. And I very gingerly sort of lift the cover on the possibility that our children or our children's children will someday have to consider the necessity of managing what the ocean actually is doing, maybe managing what the whole planet is doing. I have been slammed, absolutely slammed in multiple situations over even suggesting such a thing, but I think we have to consider the possibility that it may come about, and we are nowhere close to having the sophistication, the insight, the knowledge, the awareness of downstream effects of anything we do to actually do something like that now. And so that becomes a very delicate issue of not just philosophy, but also ethics. I mean, what are the ethics, if you think about it, what are the ethics of somebody who can precipitate rain on command? What happens to the people downwind who don't get the water that was squeezed out upwind? And we're all downwind from one another. Every nation on the planet is downwind from all other nations in one sense, and from themselves. So what we do on this planet isn't just a Michigan issue. It isn't just a U.S. issue. It isn't just a sort of developed nation issue. It belongs to everyone. And so it's very, very important that we have deep-seeking dialogues on where this can go. And when scientists begin working on a particular project, most of them like to think of defining what the system is so they can look at inputs and outputs and begin looking at how the system behaves. And to some extent, that's really what we're talking about here. And I would like to say that I think our challenge is to optimize the benefits and to mitigate the risks of basically living on a planet that's driven fundamentally by only two processes, or two energies. And the first of those is one that you're fairly familiar with. Saw it this morning before you came in, and that's the solar energy. And think about it. What does solar energy do? Many, many things, myriad things. But it's responsible for moving a great deal around on the surface of the planet. Everything from heat to chemicals to particles to water to cloud formation of all sorts, storms, erosions, you name it. And photosynthesis and carbon cycling are not small in that sequence. And so the energy from the sun drives this cycle, and energy from inside the planet drives I won't call it a competing cycle, but the energy from inside actually drives a host of additional processes. And depending on who you talk to, you could say that the internal energy basically drives many of the facets that I've listed here. And I won't read them to you because I'm sure you can read as well as I can, but I want to point out that a couple of the things that are mentioned here, metal deposits, major earthquakes, volcanic eruptions, and chemosynthesis, are all areas of cutting-edge research in one form or another. And they are related either to hazards or to potential opportunities for any number of sectors of our society. However, the human element has begun to be felt since the 1820s, the Industrial Revolution. Human activities have been affecting the way the Earth system functions. And we're increasing the ocean's vulnerability. And I want to be really careful here because a lot of people talk about, oh, are we killing the ocean? We're not going to kill the ocean. The ocean will endure. I mean, it has survived asteroid impacts. It's survived many, many things. The Permian transition is all sorts of things that the ocean has survived, so to speak. What's at issue are some of the biological systems on the surface of the planet and on the continents. And so I would say that there are a number of well-meaning folks who worry a great deal about, is the ocean okay? The ocean is very resilient, and it is, bottom line, this is a microbial planet, and we are visitors, in a sense, if you want to look at it geologically. So it behooves us to gain enough insight to make sure that whatever comes down the pike is something we can, one, anticipate, two, cope with, and three, survive, whatever it is. And that's worth considering. And at the heart, at the base of all these considerations, is a deep and full understanding of all the myriad marine ecosystems that actually make up this complex system we call the global ocean. And I want to emphasize again a point that I alluded to but didn't emphasize earlier, that it's a problem for the global society. No nation any longer has the ability, the strength, the power, the money, the tenacity, or the commitment, whatever, to actually fully get to the point where we understand the global ocean. It's going to take a global community, a global village, if you like. And just to remind you of where we are, these are CO2 contents in the atmosphere back for about 400,000 years. And then you can see the spike that is very current. And you all know, of course, about the Mauna Loa record. And it's continuing. You can see even a slight increase in slope there. What's going to happen to that? We don't know. What are the effects of having that buildup? We have a pretty good idea. So that's one of our dilemmas. This discussion is not about those issues, but there are 3 or 4 issues that are like 500-pound gorillas in the room. If we talk a lot the way I'm talking and we ignore the 2 or 3 gorillas, 2 more I'll mention to you, we're making a mistake. That doesn't mean we can go over and solve the gorilla by tapping it on the head and say, here, lie down, big boy. It's not that easy, for sure. But here is just a glimpse, by no means a comprehensive rendering, but a glimpse of the complexity that exists in the upper ocean, driven mostly by solar energy. And maybe I have 10, maybe 15% of the myriad processes that operate in the ocean. And the most important thing for you to realize is they don't just operate, they interoperate. So when one process shifts, frequently it shifts other factors as well, and they react. For example, change the pH, big changes. Change the oxygen content, big changes. Change the total amount of heat, big changes. And here in mid-continent, you are much, much more familiar, just on a day-to-day basis, with the atmosphere, and perfectly understandable. It's the part that gets cold, it's the part that gets hot, it's the part that rains on you. It's what basically wets your crops and creates drought. There's good evidence that the Dust Bowl period in the mid-30s, the 1930s, was directly related to anomalous conditions in the Indian Ocean. So it's a global system, be aware of that. But let me also remind you that there's more total heat in the upper 2 meters of the ocean water than there is in the entire atmosphere. So be aware that although the atmosphere can be viewed as the messenger from the ocean to the continents, it is just that. And it continues to move and goes back over the oceans, passes over the continents, does whatever it does, gets warmed up, heated, cooled down, lots of processes in that evolution. But mostly in the ocean, the atmosphere spends time over the ocean and comes in some sense to equilibrium with it, fairly close. In the southern hemisphere, it's even more the case. All right, so we've looked here at the solar influence. Let's look at the other side of the coin. The lower portion of the ocean is the place where there's the most direct expression of all the dynamics of the Earth's mantle. And the Earth's mantle is constantly, restlessly in motion, as you've heard in any number of accounts of the dynamic Earth, or the restless Earth, or the big earthquakes, or the volcanoes, or however you want to frame it. Even the continents are moved around by this process. And therefore the shape of the ocean basins changes as a function of plate tectonics driven by the internal heat. And there are a whole host of really fascinating processes that are spin-offs, but the deep ocean is not necessarily dominated. The deep water part of the ocean isn't necessarily dominated by these processes, but it is, at times, it is influenced. And we don't know to the full extent how much that is, because we have not adequately quantified those linkages between what goes on the bottom of the ocean in terms of thermal output from the mantle below and what actually is absorbed by the ocean. So those are major flux questions, and they're episodic questions. It changes. Everybody knows or discovered how powerful volcanoes can be when Iceland kicked up and started erupting, and it changed the travel patterns of a whole host of very wealthy people in Europe, and they were incensed. I mean, my God, these Icelanders can't control their own volcanoes. This is. So I've heard that type of thing, and admittedly, it's a bit of a joke, but try controlling a volcano sometime. Just go to Hawaii and sit there on the edge of the caldera and point and say, "Quit." It doesn't work. The Hawaiians tried that with even more attractive inducements, and it rarely worked. Okay. Complexity. I love this slide, and I love this giant screen that you have, and the projection and the high resolution that you've offered. I want you to look carefully at various parts of the system. This is just sea surface temperature. Sea surface temperature. It's 1 year worth of data, and it cycles. It's a video loop, and it's just cycling. But the point is to look at the complexity of the eddies and the vortex shedding and the equatorial countercurrent there west of South America by the Galapagos, and look at the part east of East Africa. Really complicated behavior. And you're only seeing the complexity at the boundaries of some of the color regimes. But the complexity is there all the time. And this is a global system. This is obviously a turbulent system, somewhat chaotic, you might say. But then think about it all the way down to the scale of a whale swimming, or the scale of a copepod creating turbulence so that it can pluck the particles out of the water to eat. There's there's turbulence and complexity at all the scales that you can imagine in this system. And that's only one variable. It's only one variable. There are many other variables. Many other variables. And they're all linked to one another. So when you have a system at a global scale that's this complicated, and you begin to believe that it's that complicated at least down to the scales of zooplankton, then you begin to get a sense of how complicated this life support system is that we have. And I'm going to overstate this for a second. It just occurred to me this morning as I was waking up at 5 o'clock for some damn reason. Think about the astronauts when they stepped out of the lunar lander module, and they had their spacesuits on, and they had that little backpack, that little white backpack. That was their life support system. If that life support system for some reason failed, they didn't have a long time to survive. We have a life support system on this spacecraft that we're on, called Earth. Everybody we know and love is dependent upon it, and we really don't understand how it works. So this is not a small issue, nor is it one that I find that oceanographers the world over are making a significant argument about. I think it should be much more on the forefront of people's thoughts. But the ocean is more or less out of sight, and certainly often out of mind, unless you are a surfer, or you go for a holiday, or you do things in the ocean that are mostly pleasurable, or you go fishing. It's much more profound than that. And just to give you a supplementary bit of insight, here is You've probably heard of what do they call it, a food chain? Well, it's not a chain, it's a web, and it's an incredibly complex web. And there's some growing evidence that if you modify some portion of this network or this web by removing one species, it'll shift. And it's not clear how it will shift. It will shift. That's been proven. I mean, the evolution of life on the planet makes it clear that something like this clearly shifts over the millennia to eons. But if you, say, remove some of the top predators, or you induce a situation where the acidity of the ocean begins to render coccolithophores unstable because their carbonate shells are dissolved instead of precipitated, that's the base of the food chain. And there will be changes, and we don't, that's my point, we don't know what those changes are going to be and how they will induce other changes. But be aware that as much as, and I'll touch on this a little later, as much as 50% of the CO2 that's been generated by the fossil fuel conversion has been absorbed by the ocean. By the same token, nearly 1 in 2 oxygen molecules that you breathe in this room right now were produced by the phytoplankton in the surface of the ocean. So the role that the ocean plays for us is out of sight, but I don't think it should be out of mind. And this is just a quick overview of, everybody's seen this before, but I wanted to point something out that I find really quite fascinating. I wanted to point out that there are a lot of analogous areas on the planet. You don't just study one place and then you get the answers to that one, and then you go off and do something else that's really different somewhere else. It's like plate tectonics. If you study one plate relatively well, and then you look for comparisons with other plates, you can learn a great deal. But if you all study them all sort of superficially, then you never get to depth on that particular topic. Similarly, here, look at the gyres. These are driven by the winds, and they're obviously constrained by the ocean basins. So you would say, well, southern gyre and the northern gyre and the Pacific. Well, the part where the water goes north and then comes south and goes to the west, that's a gyre, and it's similar. The processes that operate on the west coast of North America or on the eastern boundary of the Pacific are very similar here. The water is moving toward the equator. The water is moving toward the equator. These are known as eastern boundary currents, and in those areas, here and here, there are major fisheries. And there's what we call wind-driven upwelling. The upwelling along the continental shelf supports massive fisheries in all of those environments. So by studying one of them well, we begin to get insights into others. That's important to bear in mind. Okay, I mentioned this earlier. I won't beat this one to death because you really, if this is something of great interest to you, there's a huge amount of material written on it, and I urge you to avail yourself of that data. But what this diagram is intended to show is that there was a normal cycling before the Industrial Revolution, and then with the Industrial Revolution there's been strip mining, there's been massive output of fossil fuel conversion, and a whole host of processes that have really dramatically increased CO2. So that diagram I showed you, where the CO2 in the atmosphere was so much higher than it had been for 400,000 years, if the ocean hadn't been there to absorb it, would have been even higher. And therefore the warming would have been even more profound than we see now. Now there's also, in my view, this is personal perception, there's also an urgency to this, and I'm not trying to say that spending all your money on oceanography is the only thing you should do to solve all the problems of the future human race. Not saying that at all. But it is one of the parts that has been largely ignored. And one thing to bear in mind is that, roughly 3 weeks ago, we passed the 700 billion mark. 7 billion mark. Thank you very much. I'm so glad you came. It's the 7 billion mark of population on the planet. And in round numbers, about 1 in 7 people are seriously undernourished, and about a third of those actually are close to starvation. Okay, for those of you that are in your 30s, by the time you're my age, I'm 70, we're going to be going from roughly here to roughly here, and there's going to be another 2 to 2.5 billion people on the planet, round numbers, unless there's some Malthusian disaster that actually dramatically reduces population, which we hope doesn't happen. But if that plays out, where will those people be? Well, they're likely not going to be in Ann Arbor. They're probably not going to be in the Berkeley Hills. They're probably not going to be on the left bank of Paris. They're going to be in the areas where already it's very difficult to feed the people that are there. And if there are dramatic changes in the way the ocean behaves, then there will be dramatic consequences on the continents. So let me share that with you here. The importance of the oceans emerges here, and I want you to look carefully here at there's a timeline here. It's clicking along in 1982 to 1998 and then cycling again. And it's sea surface temperature, again, the same variable I showed you earlier with the richer colors. Red is warm water, blue is cold water, relatively. And on the continents, there are, bright green is growth of vegetation, and olive green or brown is dieback of vegetation. Okay, now look at what you can see in the equatorial Pacific, obviously, are El Nino, La Nina cycle. El Nino red, La Nina blue. And you see them on sort of a regular basis. It's the cycle is, it's not entirely regular, it's somewhere between 3 and 7 years. And it's a complicated thing, but it basically, there are a lot of complexities associated with it. But look on the continents, say, for example, just to focus your eye for a moment, look at the Horn of Africa, and look at when the Horn of Africa turns bright green. It only turns bright green during an El Nino La Nina cycle, which is something that is most profoundly effective in the Pacific, which is half a planet away. So if you don't think there's some correlation, and I'm not saying there's a one-to-one cause, although I believe that, I'm not saying it because the evidence isn't conclusive. But there is a correlation between the rhythms of the ocean and its surface temperature distributions and the kinds of patterns of rainfall and drought on the continents. And we don't know very much about those linkages, and we don't know very much about how the rhythms of the ocean are determined precisely. And we don't know very much about how they change. Nor does this data set extend over a long enough period to look at things that are longer wavelength than El Nino, La Nina cycle. For example, there are decadal oscillations that might take place every 2-3 decades triggered by other phenomena, and then there are even longer wavelength phenomena. And the question then is, can we anticipate enough so that we can see problems coming that are going to result in serious reduction in the food production in a particular area? And can we cope with it as a global society? Those are the kinds of questions we should be asking ourselves and putting a lot of energy into understanding. And there's a lot of basic research involved here. There's a lot of applied research involved here. There's a whole host of research that could be part and parcel of this. But we do need that kind of activity. Now, I'm shifting gears a bit into the world that I know a little bit better, and that is the rocky part, the hard part. And everybody, I think, in the room has probably seen this before, but I want to emphasize how amazing this is. A picture of the youngest rocks on the planet as shown here, and they are mostly in the ocean basins. And you can see there's a symmetrical sort of behavior here. And we'll talk about that in just a second. But somewhere along this feature, the volcanoes are erupting continuously somewhere on the planetary features. 70,000 kilometer long feature. It's the largest feature on the planet. And it is not just a mountain range, it's a volcano. And molten material from the deep earth is rising along that fissure all the time in some fashion. It doesn't always come out on the surface all the time, but there is and there has been. And so the ages here are, we call it zero age, but it could be as much as 1,000. You could go to a particular place on the seafloor, maybe not here, but over here perhaps, or right in through here where the spreading is slow, and you would find rocks that might be 100 to 1,000 years old. As you get further and further away, you get into older and older rocks, and these rocks are around 200 million years old, as are these blue rocks. But the ocean floor renews itself on a regular basis, and it moves the continents around, and it forms these mountain chains here, where the subduction, that plate, the Nazca plate, is being subducted beneath North America or South America, and creating the Andes. So it's a pretty exciting situation. So let's fold the plates in on top of this picture. Watch closely because I'm going to do this slowly. The tectonic plates have a 1-to-1 correlation to the spreading center. So if you would understand this planetary scale phenomenon, you need to understand how the plates work. And if you would understand how the plates work, you need to choose a plate to study as thoroughly as you can, and then look carefully at others. And just to help you decide which plate you want to study, I've colored them differently. Anybody for the Juan de Fuca tectonic plate? Because your tax dollars are already paying for the study that we will launch there. I'll come back to that. But you see the point. It's an interesting transition to realize that the dynamics of tectonic plates, driven by the restlessness of the deeper earth, and remember, under the oceans, which have crustal material that's only about 5 to 6 kilometers thick, all made up of basaltic material, are really very different than the continents, which tend to be 30 to 50 kilometers thick. And so the mantle dynamics are not expressed very directly through the continents, but they definitely are through the ocean crust. So that's a great place to study the deeper earth. And I just wanted to show this to you more out of, I find it curious, and I just wanted to show it to you, and I knew Henry was here, so I wanted to share this with you, Henry. I have a question about this. I don't have an answer. But watch the patterns of earthquakes. Now, the earthquakes are indicated by the position of the balls, and they expand when the earthquake actually goes off, all right? And the little red wedges are active volcanoes. So watch, you can see over here now. And you saw Chile, and you probably saw the Sumatra. But look at the difference between the last 10 years and the first 10 years. It seems to me there's more activity in the last 10 years than there is in the first 10 years of this 40-year sample. And that seems strange to me. But maybe it's not strange. Maybe it's just we're starting to get enough data to get enough of a perspective to find that earthquake activity actually varies for reasons that have to be fascinating. And I don't think, I want to point out that over here you get an indication, these are magnitude 6 are the smallest ones we have on here. And ever since people began worrying about nuclear test ban treaty type activities, we've been able to pick up magnitude 6 earthquakes worldwide. So I don't believe, and I'm not a seismologist, but I find this really fascinating. And just to give you a flavor of this is a very rare event you're about to see. You probably saw it on the news a couple of years ago, but I just wanted to remind you of an underwater volcano erupting. They're very, very rare. We rarely capture an underwater volcano actually erupting, and we're never there ahead of time, and we're never there afterwards in detail. We don't get detailed information about how volcanoes erupt, and yet a very large fraction of the volcanic activity on the planet is dominated by underwater volcanoes, 60 to 70%. So here's West Mata, and here's what it looks like in its glory. It's about 700 meters deep. We're looking out through a high-definition video camera that's on an autonomous vehicle, or rather a remotely operated vehicle called Jason, and it's in the Western Pacific. Now, all the processes that are operative there, they look fascinating, but think about it. 3 billion years ago, the size of the continents wasn't as big as it is now because they have grown through time. So it's arguable. I love it when it's arguable. That means you can make a statement and not necessarily be right. That one of the most common phenomena on the planet is the eruption of molten rock into the bottom of a global ocean. And many people think that it may have been directly correlated early on in the evolution of the planet with the origin of life. So there are some very fundamental things that are directly related to the ocean that may not affect you day to day, but they're pretty fascinating because if we begin to understand a little more about how the ocean, how you doing? How the oceans evolved and how life evolved on this planet, maybe we begin to understand things about other planets. And I also wanted to show you that this is the icing on top of that layer of molten rock that is basalt, that is the oceanic crust. It's created at about the speed your fingernails grow from the ridges. On top of that are all of these volcanoes, all of these seamounts, like Hawaii, and there's a lot of them. There's over 100,000 volcanoes. So volcanoes on our planet are pretty impressive units, and they, I think, demand a lot of attention. Just to capture some of the thoughts, somewhere between 60 and 70% of the world's volcanism occurs underwater. Mid-ocean ridges create about 2/3 of the planetary surface about every 200 million years. There are hundreds of thousands of underwater volcanoes and seamounts. Many of them form very close to the ridge crest, by the way. So that as the plate spreads away from the ridge crest, these volcanoes form. And very few of these have ever been really witnessed, and you've just seen one. They are a source of important metals, and they may be a source of very potent exotic microbes, some of which have enzymes in them that may function close to 100 degrees centigrade under pressure, under certain chemical conditions. So we're talking possible effects for industrial issues, and that's a long and complex discussion and a very fascinating one. So, a quick look at the Juan de Fuca tectonic plate. A cross-section through the Juan de Fuca tectonic plate shown here. It shows the basic processes of plate tectonics are displayed in sort of a microcosm there. Many of those processes operate all over the world. One of them, the spreading centers, frequently what happens is the mantle beneath the ridge crest is constantly rising and then spreading, and some fraction of the mantle partially melts, and the melt is a little more buoyant, and it rises and collects into what we call a magma chamber, a puddle of 1,200 degrees centigrade molten rock, maybe a kilometer or 2 or 3 below the sea floor, which is here. Okay? And suffusing this entire volume are, we now know, microbes of various types, some of which are rare and have unusual behavior. And this is a picture of what downtown hydrothermal city looks like. This particular, from here to here, is about 25 meters. So these are serious pillars. They are covered mostly with animals that live off of the diffusion of the hot water, which is in the center, diffusing out through the wall. But a lot of the hot water gets to the top and comes out as this plume. This particular feature, this is called fin, this is called Rhone, and this is called Fang. All three of those are currently in the American Museum of Natural History. That's another story that we can talk about later if you like. But out of this one, we found the highest temperature microbe that has ever been recovered and cultured. It's 121 degrees centigrade. And this is what the cover on the surface of these looks like. This is a high definition image of the video, or a video image of the tube worms that are very common coating the outer surface of these structures. And these have no mouth, no gut, no anus. They have a body cavity called a trophosome that has microbes embedded in the wall and they're endosymbionts, and the creature basically supplies vent fluids with nutrients in it down into the trophosome. The microbes multiply, and then when the tube worm, quote, gets hungry, it absorbs some of the microbes, and so it's a symbiotic relationship. It's a deliciously complicated and very fascinating system. At the other side of the tectonic plate, those are on the leading edge of the plate, on the plate that's being subducted here beneath North America, where the lithosphere plunges beneath North America. There's a lot of things go on here, the Cascades, for example, or the Aleutians, or the volcanism associated with the Tonga Trench, or the Andes, all similar to this. But over here is some interesting activity where the plate moves across and down. The sediments that accumulate on the floor of the plate, of the sea floor as the plate moves, are sort of scraped off by the snow plow of the continent. And this is a seismic cross-section. You can see the sediments are still flat lying out here, but as they encounter the continent, they are both compressed and compacted, and fluids flow out continuously from this accretionary prism is what it's called. And some of those fluids are very rich in carbon, and there are microbes that live throughout the layer of sediments that actually are methanogens. So they take that carbon material and they convert it to methane. So there is massive amounts of streaming methane off of this system, and some of the methane at the right pressure and temperature will freeze into something that looks like this, and many countries nowadays are looking very carefully at gas hydrates or methane hydrates as a potential source of both energy and a potential threat. You're well aware, I'm sure, that methane in the atmosphere is as much as 25 times more dangerous than CO2 in terms of a greenhouse gas. So a massive release of a large amount of this methane over a subduction zone, for example, could actually, in short term anyway, have a significant impact on global warming. And whether that happens, whether it has happened, whether it will happen, those are issues that a lot of research is going into. But at the same time, folks are looking at it as a potential resource. Now, this is the way we did oceanography. When I was young, this is how we did oceanography. It was a lot easier. You didn't need to get a big grant. You just had to have two uncles that liked to drink, and it was okay. It wasn't bad. And if you were curious, you could, as long as you could hold your breath, you could look at things that other people didn't look at. But the National Science Foundation decided that we should move on, and they are funding a very serious investment called the Ocean Observatories Initiative. And it's because of the reasons that I've talked about. I won't reread those things to you. I've ticked them off in the first 3 bullet points there. But let me talk with you a little bit about this initiative, because many of us in the oceanographic community felt that what we were doing was great, but it wasn't enough to get where we wanted to go. Now, high latitude observations, like the 2 shown here in the southern hemisphere, are part and parcel of the Ocean Observatories Initiative, and they involve satellite links to 2 or 3 clusters of moorings that will have mobile platforms like gliders moving around in the vicinity, and they will be placed in these locations for 25 years. And the data flowing back will be at the kilobyte to tens of kilobyte per second, and they will be supported initially by batteries, and then hopefully by solar power and maybe by wind power. So they'll become greener and greener and greener as they go. But the focus, scientific focus, is on air-sea exchange in these environments where very little information is available, because the winds are so strong and the waves are so powerful, and the bubbles that are created when the waves break are wafted downward by something known as laminar circulation. And those bubbles then come to equilibrium with the surrounding water. So it's the way that water and atmosphere exchange gases. So doing work at the high latitudes where it's most extreme is very important. We have 2 more of those in the northern hemisphere as part of this OOI program, in the Erminger Sea and Station Papa, which has been occupied since the end of the Second World War by the Canadians. Emergent Sea is the place where the deepest North Atlantic deep water is formed. It's the result of very saline fluids in the Gulf Stream migrating far north enough so that they become cold and they sink. And at that point, they are more dense than the surrounding waters, which are not quite as saline. And so both of those process studies are taking place in both Station Papa and Emergent Sea. Then the Pioneer Ray, which is on the East Coast, is a mobile platform that will be in place for something like 4 to 5 years, and it will study process-oriented oceanography. In this case, it'll look at the activities right at the continental shelf slope break and right where the Gulf Stream moves north and the Labrador Current, cold water from the Labrador Current coming south, how the exchange takes place between those two water bodies and at the edge of the continental shelf. So that's a focused area, the Pioneer Ray, because it will move. The endurance arrays and the regional scale nodes in the box on the west coast is the part that I know a bit more about. So with your permission, even without it, I will focus primarily on the activities associated with that system. Now, the vision for the entire program is to launch an era of scientific discovery and understanding within the ocean basins using 3 key words, 3 key capabilities. One is accessible, meaning everything we do is going to be hardwired to the internet. 2 is interactive, meaning everything that we detect offshore, wherever we can detect it, can allow us to reconfigure the assets that we have in place in order to track whatever that activity is. A volcano erupting, we can change the frequency with which we're taking samples, we can move platforms around, we can do all sorts. So it's interactive. We can detect something, and even though no human is there, we can actually react to it. That's very powerful. And then finally, it's kind of tele-presence, because humans can be in the loop if we're more and more successful with cyber infrastructure. By the time many of you are my age, you know, many of the decisions will be much more routine. But hopefully we'll still need humans eventually to log the information and respond. Decisions early on as to how and when to launch a response, because responses won't be cheap, will be important human involvement. And I believe folks around the country, one of the things I want to add is that everything we're doing is connected to the internet. We would be able, for example, to work closely with groups from this university or any other university mid-plate, so to speak, to actually be involved in the decision-making, to actually develop an oceanographic engineering side to this program, which is not bound by the shoreline. That's where most of the natural accumulation of oceanographers on the planet is near the shoreline, but it's no longer necessary, any more than it's necessary to be in the coastline in order to tweet your neighbors. You know, it's a global kind of connection that we're seeking. And what's the science that can be done? It's almost endless. It's almost unlimited. But I will show you a few things, just capturing your imagination, but not necessarily, by no means is this covering the full spectrum. But with the same facility off the west coast, that is the cabled system, we would be able to look at 5 to 10 different water column processes and 5 to 10 different seafloor processes using the same infrastructure, the cabled system. We'll come back to that in a minute. But certainly climate change and all of its aspects as associated with ecosystem dynamic shifts caused by things we see in climate change, that's certainly accessible. Ocean acidification is more seriously expressed in the Northeast Pacific than it is anywhere else on the planet right now. So we'll be doing detailed work with our colleagues at NOAA on those kinds of things. Dissolved oxygen is killing fish, and this happens at many of the output sites for large rivers. We think it may be related to excess use of fertilization. We don't quite know. There could be many reasons for dissolved oxygen, but it definitely does harm. The carbon cycle, represented by this beautiful coccolithophore, is expressed in many different ways, and it's one of those things that has myriad processes associated with it. And so we have the potential to do completely thorough, detailed studies looking at tens and tens of variables throughout the volume of the ocean for 25 years, which is the timeline that NSF has identified for this program. So we have decades of study, and we have massive amount of bandwidth and power. And then finally, coastal upwelling, which drives a lot of the fishing activities. There's a whole host of those. I just talked about gas hydrates. Most of you know something about seismic activity just because you read the newspapers. But seismic activity in all of its glory off the west coast could range from just tiny little mechanical burps, if you like, along little tiny faults, to volcanoes getting ready to erupt, to volcanoes that are erupting, to major earthquakes on subduction zone megathrusts. Bathymetric forcing, this is a very important one that many people don't think about, but if you think what it would be like if you were standing on the plains of Nebraska, sort of just standing there, compared to what it would be like if you were standing on the top of Mount Rainier, you realize that where you have a relief, you are liable to intensify the winds because the air flows over, it's an orographic effect, the winds flow. Same thing happens in the oceans. There are intense effects of having rough topography, say, or high topography. And that causes mixing, and the mixing of the deep ocean is one of the great unknown areas. So that's a wonderful area of research. Then spreading centers, I'll talk a little more about that, and subduction zones, you can imagine with the kinds of things that could go on there. Here are the kinds of capabilities. We'll have moorings of various types. Here's an example of a mooring here and here. These are the facilities that we would have in the locations that are high latitude, here, and to some extent here, there'll be this type of setup, but it'll all be satellite linked. There's no cables involved. Off the west coast, this is Vancouver Island, Seattle is somewhere right in there. Off the west coast, we have worked with our Canadian colleagues in Neptune, Canada, and we've taken sort of the southern two-thirds of the Juan de Fuca tectonic plate and laid fiber. This past summer, we laid 900 kilometers of fiber across the Juan de Fuca tectonic plate and then down and back up the continental shelf there. The kinds of things that we'll be studying, and I don't want to beat you all to death because I know that you're more into cyber infrastructure than you are into this kind of scientific driver, but if I were playing my cards just right, I would try to seduce some of you across to the light side, where science is involved. Sorry, Dan, I mean, you let me in the door, you should never have done it.
You're right.
But there's some really exciting things that are in the offing, and we desperately need and are going to be totally dependent upon computational power in all of its facets. Everything from how do you store petabytes per day, to how do you sort through it, to how do you compare it to models that we already have, to how do you do command control operations offshore where no one is present and you're running the whole show from, in this case, Ann Arbor. It's not, I mean, if we can run it from Seattle, you can run it from Ann Arbor. I mean, anyway, these are the sites in the Monterey Bay here, and each of these represents an installation right now that's in the Northeast Pacific. So it's becoming the most intensely instrumented portion of the global ocean, and a lot of processes are taking place there. Here's a close-up view of the solid lines are the places where we have funded fiber that's in place now, and we will be putting in these secondary nodes, these primary nodes this summer. This is axial seamount on the spreading center, Juan de Fuca spreading center. So axial seamount's right there. And Hydrate Ridge is right here. It's a gas hydrate deposit. And these are some of the coastal processes where the Oregon State folks are working very closely in their coastal area. And these are uncabled right now. That dash line indicates an expansion potential for cabling. And these sites will have the moorings that have battery power and satellites and autonomous vehicles. Then our colleagues, Neptune Canada, have laid this fiber in place, and they are receiving some data from some of these nodes, and they're soon to receive data from all of them. So that's a quick overview, and here is the key. Abundant power and unprecedented bandwidth in the environment. If you go to a university as a young professor, or as a technologist, or as an engineer, you expect electrical power and high bandwidth in order to set up your laboratories. If you, a university that couldn't offer you that wouldn't be as attractive as one that could. We're now saying that we can do that in the ocean. We can give you direct connectivity to the internet at high bandwidth and a significant amount of electrical power. And this is what we're committed to delivering and have the funds in hand to deliver. I'll let your, I don't have to read these to you because you can all read better than I, but let me emphasize a couple things. We have a lot of expansion potential. We have also extremely good timing. We will be able to resolve microsecond timing on these detection systems, which allows us to do very sophisticated seismological studies and, I might say, acoustic tomography of various types. So there's a lot of potential here. This is the cyber infrastructure group is at UC San Diego. The head person there is John Orcutt. He's the principal investigator for the cyber infrastructure component. And I urge you to contact folks if you're interested in pursuing the coastal global component of this thing. I urge you to get in touch with Bob Weller, who is from Woods Hole Oceanographic, and he will give excellent lectures on the potentials there. There are some scientists at Oregon State. Jack Barth would be one that you could contact on to deal specifically with some of these processes here. So there are a lot of folks, and then at the top level in Washington, D.C., Tim Coles, who is the overarching principal investigator for the entire program. He is at the Consortium for Ocean Leadership, and I urge you, if you want to follow up on some of this in other ways, to connect with them. Now, so we call this regional scale nodes. It used to be known as Neptune, but now we call it the regional scale nodes, which is this system in white. And I want to just tick through some of the capabilities. These gives you the design facts, and again, allowing you to read them rather than dictate them to you. But let's look at the primary node here. Here's what a primary node actually looks like, and this is a switching box. It allows for junctions, and it allows for control over, and at each of these there are 10 kilovolts and 10 gigabit per second bandwidth. Here's what one looks like. That's a normal human being standing in it. It's not underwater here. And then this is the electronics package. It's a trawl-resistant system that sheds fishermen's trawls, at least to some extent. And then the electronics package can be put in and out by a research vessel. The secondary nodes, you can see the primary node there. Here's a secondary node here. And the secondary node steps down to 375 volts and about 1 gig E. And that's what you have here. And then you have little, up to 10 kilometer, usually less, extension to a seismometer, for example, or a mass spectrometer, various other systems. The sensor networks, again, seismometer here. There are a whole host of different sensors that are part of the system. And here's an innovative component of the whole system. We will have complementary moorings, one of which is two-legged mooring, and it's a platform at 200 meters below the seafloor, below the surface of the ocean. And it will rise and fall here under great control. That's this thing. And then the full ocean platform from over here, which starts at 200 meters depth and goes all the way down to 3,000 meters. So that's a deep profiler. It doesn't move as fast as this one, but we can control its depth as well. In here, give you a sense of what that might involve in terms of studying the ocean. Now, there's something called thin layers, which seem to be accumulations, in this case of, I think Calanus pacificus anyway, those are copepods. And they tend to form in shallow layers, and we don't, or thin layers, I must say. And those may be shear layers between two water bodies or water masses. We need to understand those better, and yet what this thing allows us to do is to search, find items of interest, and then focus in on them and begin to study them in great detail. And it has something like 12 different sensors on it, so that can be turned on or turned off, or possibly downstream, we may be able to even sample. And then over here at the other end, where is it? Here, this fish system, there it is. This one can also be controlled, and that's the full water column. So we're going to cover the water as thoroughly as we're going to cover the sea floor. Now, let me just show you quickly what it might look like if we were going to study this volcano. What would the array of instruments look like? This is axial volcano. It's on the axis of the spreading center, which is spreading about 6 centimeters a year, about the speed your fingernails grow. And this volcano is like Iceland. It's a big cluster of additional volcanic activity that's right on the spreading center. And in the top of the volcano is about 1,500 meters deep. The surrounding dark blue color is around about 3,000 meters deep. So that this thing is a 4,500 foot high volcano. And this is a caldera. It's a depression in the top where magma has moved up and down and created this depression in the top. And we will be hardwiring that system with all sorts of things. And this is a quick overview using animation to give you a feel for it. This is an earlier edition, but that's the deep profiler, and then the shallow profiler is in the same platform. In our final analysis, we'll have the two-legged system, but this gives you an early view. And then we hope to have, in time, these aren't immediately paid for, but we hope to have autonomous vehicles that will be patrolling the environment. We will have, these are paid for, they're different kinds of instruments in a little robotic colony on the seafloor, all of them hardwired to the internet. And then we'll come right past this one, which is searching, and it'll have 6 or 8 variables on it, or sensor packages, and then into an area that's close to a hydrothermal site, and I'll show you what sensors we're talking about there. And you can imagine keeping all this sorted out. You can imagine having the data coming back from each of these sensors in all its glory and being recorded and made available within seconds to anybody around the country on demand. So, that's the flavor of what we have in place. Not in place, but that's what's been funded, that's what we're building. Now, what Marcel Proust made clear to many people about over 100 years ago was that the real voyage of discovery consists not so much in seeking new landscapes, but in having new eyes. And he meant this metaphorically. It's probably true metaphorically, but it's also true specifically and explicitly in terms of technological evolution. So I wanted to give you a flavor of where we might be going, since many of you are early to mid-career and you have the potential with this high power and high bandwidth in the environment to dramatically change the face of how human beings study the global ocean. The key point is that there are many emergent technologies, rapidly changing technologies, that are being paid for outside of oceanography. And many of them, with the cabled observatory, could move very quickly into being oceanographic sensor packages. If we can pull many of those in simultaneously in the next 5 to 10 years, there will be an exponential growth of the capacity that human beings have to project their presence into this global ocean that is so important to us to understand. Now, this looks a little busy, but it is. Power delivery from the environment is rapidly changing from the ocean. There are wind-driven turbines that are offshore. There are wave guide systems. There's any number of different kinds of capabilities. They're not very mature right now, but they're moving rapidly. Within 10 years, we probably aren't going to need to send electrical power out on the fiber. We may be able to extract enough energy from the environment to actually run our experiments, and then the fiber is only a bandwidth system. Robotics is moving very, very rapidly. And there are a lot of drivers for very sophisticated robotics. We need to move any number of these robotic systems into the environment, and we can do studies of all sorts. Ecogenomics, this is a revolution in its own right. The ability to do genomic analyses in the environment, thanks, frankly, to the Human Genome Project, which was supposed to take 30 years and took 10. Why? Because the rate at which the processes necessary to sequence genes became shorter and shorter and shorter, and the size of the systems necessary became smaller and smaller and smaller, and to some extent cheaper and cheaper. It's a kind of a Moore's law type activity, but it works for sequencing genes. And there are several folks, Chris Scholen among them at Monterey Bay Aquarium Research Institute, who have systems that they have tested at depth that can actually do genomic analyses remotely with no human being in sight. So we're crossing this threshold together, both with the technology of the cable and with this incredible capacity to do research without being there into the genomic systems that are part of a marine environment. This one, everybody in this audience knows about this. I mean, you know more about it than you think because you carry this around in your pocket. 15 years ago, you wouldn't have had anything as sophisticated as this. I mean, I could take a high-definition picture of you all right here if I stopped for 10 seconds. And it's important to realize that this is what you have in your pocket is trivial compared to what's being researched. They're going from high-definition video to 4K, which is 4 times or greater, and the Japanese are pushing it much, much beyond that. And we will be doing that in stereo soon. So before long, you will be able to be somewhere mid-continent, say Ann Arbor, for instance, and you would be able to tune into a set of cameras over which, if you had the right kind of grant and the right kind of permissions, you actually could control where it goes, and maybe it's on a mobile platform. You could take it and look at parts of the ocean that you want to see, and then you take probes that go into, say, a smoking black smoker system, venting 300-degree fluids, and you can take samples and look at the genome of those microbes. That's what's on the threshold here. We're not far away from being able to do that type of thing. One of the empowering elements is this thing, the fiber optic cable, or the fiber itself. And there's a long story here. I guess I'm running a little long, so I want to wrap things up quickly. But let me just simply say that this is almost as magic as the computers that we have come to just assume we have. And you all use cloud computing when you Google something and you get 475,000 answers to a question that you ask in about 0.2 of a second. You're all using, and imagine bringing the power of grid and cloud computing into the digestion of all this information. And then finally, nanotech is a world of huge potential, to put it that way. That's fair enough for everybody. And a few already magic events that are taking place. So I argue that having cables in the situation that they're in allow us to pull all of these different technologies, all of which have been developed outside of the world of oceanography, into the world of oceanography in a fashion that, if it's strung together properly by cyber infrastructure capabilities, will vastly enhance the human potential to work the global ocean in new and different ways. And this is important for multiple reasons. It's important because it's captivating to young people to have an adventure where they are part and parcel of the exploration. And make no mistake about it, we know pretty much where big pieces of the ocean and the ocean floor are. What we're exploring now is the time domain. We're looking at how all these things change through time with respect to one another. So it's a new kind of exploration. We need new eyes, if you will. And I mentioned 7 different kinds of new eyes that we bring to the table, and they come literally to your office through the internet. Ecogenomics, here's an example. Think this way. Some event takes place in the ocean. It could be a red tide, it could be an erupting volcano, it could be anything, a giant storm, and you decide you want to see what the effects have been on the base of the food chain. So you turn the pumps on these little laboratories that are roughly the size of a trash can at this point. And you kick the analyses in, and within a minute or two, you have genomic analyses from 6 or 8 of these different systems over an array somewhere that may be 4,000 or 400 kilometers away from where you are, or 1,000 kilometers. You have the potential within 5 to 7 years to do this kind of research, and then to interpret it in terms of all the other physical, chemical, and biological parameters that you can detect as well. Earthquakes. Here's 2 years of earthquakes on the Wanafoot Plate. It's not as if we're going to build this system and then wait for maybe something won't happen. There's lots of earthquakes. Well, every single one of these earthquakes we found from our last 15 years is related in some fashion to microbes that are issued from below the seafloor up into the overlying ocean. Exotic microbes of various types. And so we are going to be in a position with the cabled system. There's axial seamount, which I showed. We flew through a system there. And so we can look at the seismic activity there. We can determine what kind of seismic activity is taking place. If it's harmonic tremor or something like that that indicates that it might be an erupting volcano, we decide to put a box around it and we target it and we send in the troops in the form of autonomous underwater vehicles. And they fly into the erupting system. Some of them get trashed, inevitably. You don't mess with volcanoes without you know, they're dangerous, but we believe we can do this and survive. Samples are taken of both the microbes and the particles and the fluids, so we have the chemistry, and they're ejected to the surface with flotation packages and picked up by autonomous airplanes from nearby and brought back to laboratories directly, so that within 24 hours of a volcano erupting, we can have the samples of microbes as well as water and particles actually in the laboratory being studied and being converted, if is appropriate, for biotechnological change or pharmaceutical development. There's a lot of potential here. Now, one of the ecosystems of interest would be what happens when a volcano erupts. But another one is to take a box that's 45 kilometers on the side and patrol that entirely and thoroughly, so you're constantly moving through the volume, making measurements of all sorts, of all kinds of things. So you begin taking a piece of the ocean and you begin to study it as thoroughly as possible. And then when the seafloor below it erupts, then suddenly you have done your homework, you have the control volume, and you can look at precisely the impact of an underwater volcano. Why are they interesting? Because there's 70,000 kilometers of them, and nobody's ever seen them in any significant way and the way they interact with the ocean. This is a fundamental planetary process that we want to understand. A more detailed study up close, right on that feature there, is this one, and so we would have much more sophisticated robots than the gliders. These are buoyancy driven and relatively slow, whereas these can be immediately directed in any path we want. Here, for example, might be an erupting, this is the caldera, the edge of the caldera. These are moorings that are moving up and down routinely. And down here on the seafloor, you can see that one. That's an autonomous vehicle. It's moving in a routine pattern. And here's another one up here. See it moving? These are under control, and they can be programmed to know when they're in the plume and when they're not, and to move back and forth, not just sampling it, but measuring the changes in the plume. And the plume tends to level out at neutral buoyancy, just like the top of a thunderhead on a summer day when you're getting big thunderstorms. They rise up to a level at which they're neutrally buoyant. Same kind of thing happens here. But we've never quantified this. All we've done is see it, barely, trivially. So we're on the threshold. There's the cable. You see instruments on the seafloor, so we can look in great detail at what's actually going on before, during, and after. We're basically wiring an underwater volcano in the overlying ocean the same way you would wire an astronaut in outer space, so you can track all the processes that are going on and begin to understand the physiology of the entire system. I use that term loosely. I'm almost finished. I can feel a little restlessness in you, so please hang on. You remember what happened on 9/11? You probably don't remember what happened on 9/7. Well, a woman in New York City, or some doctors in New York City, removed the gallbladder of a woman in France. 2001, 9/7. Look it up in the newspaper. They successfully did it. Why she agreed to do that, I do not know. But, you know, people make the books in different ways, I guess. Anyway, they successfully did it, and it was a decade ago. Well, we have better power and better bandwidth connection now than they did then, with the seafloor, with the ocean. So we can run laboratories, if you let your imagination run just a little bit, especially if we have the computational power and control of feedback. We can run, and the high definition video in stereo, we can begin doing studies in the ocean that no one would have ever imagined before. And you can innovate while doing it. And of course there will be failures. I'm not arguing that nothing we do will ever fail. But if we don't try it, it'll never even happen. So the cyber infrastructure part links all the pieces. It's the glue, in a sense, that holds it together and brings it to the public in many ways. We have a 5-year plan. We're in the middle of the third year. And by 2014, we will have the systems together and in the water and hopefully commissioned. And then we will transition into a 25 to 30-year period where we have operations of all sorts. The marine operations, the University of Washington is responsible for building the cabled system and operating it in the early part of the period. Then it will be recompeted, as all NSF facilities are. The cyber operations will initially be in the hands of the folks from UC San Diego. And the science operations will largely be in the hands of the scientific community. And exactly how all that unfolds is something we have to learn to do. It's not as if we have decades of experience in doing this. So we are in the process of defining how this will unfold, but we're in the process of building this system here. And we expect it to evolve. We expect to have successes. We expect to have problems. And we expect to solve those problems and move on. Whew. This one was a mistake, I guess. It's too bad. There is actually a figure in here that is cut out because this is a 5.6 gigabyte presentation. and my computer just choked on this picture. I'm sorry. But it doesn't matter what this is. But the data here, the open data, there's no proprietary period. There'll be near real time. We have seconds of latencies, no more. It'll be interactive, meaning that we will have closed loop control, so we will be able to actually see what's happening and then respond to it within seconds. It'll be scalable. Basically, we hope it'll be linear. It won't necessarily be. But once the investment is made, this is important to realize. It sounds like a lot of money. It's over $100 million to put this system in. But from that day forward, the transmission and the power are there 24/7, 365 for decades. So compare that to 6 or 8 ships a year that are 4 or 5 to 6 million per ship, and they're only there for a month. So that if you calculate that out, you begin to realize that not only will we be there 24/7 during the winter, during the summer, when events take place, we will be there, which is not true of ships. It's a new way of doing business, and it's a way of doing business so that the public can watch over our shoulders as we do this. We will be like NASA, we hope. We will make some mistakes. We will have some successes, and we will share both with the public. Detoxify or demystify oceanography and science in general. The data provenance, we will always keep track. This is part of the CI responsibility. We will keep track of everything that happens to the data so that you can always trust the data that you have. And it'll be high bandwidth. I mentioned that earlier, 10 gigabit or better for openers. And finally, the social networking, we think, is going to involve millions of people, maybe more. There are people that we are not putting limits on the data so that it'll be available to people all over the world. Sorry about that picture. Okay, so here's something to think about. NSF and Canada are investing in high power, high bandwidth infrastructure in the Northeast Pacific. It's the first major experiment of this type for the United States, and it's the first comprehensive one for anyone anywhere. The Japanese do have seismometers that are hardware, but they don't, because of their fear of being hit by events that they don't anticipate, they don't allow others to become part of that. So other scientists can't be on that. The cyber infrastructure community can play an early role in helping to validate the concept of how this next generation oceanography will play out. this could be very powerful. I'd love to talk more about that. I consider it comparable to launching Sputnik. For the first time, we could see the Earth from outer space. For the first time, we can see the ocean from the inside out on a routine basis. And there are challenges and opportunities and new ways of seeing here. There are lots of opportunities, and if you're a scientist, you can let your eye run down this page and let us know what part of it you're actually interested in, and there are many, many, many others. I would like to see folks come up with gaming approaches. How could you game the ocean? You know, you're competing with people to find new hydrothermal sites, or you're competing with people to find the most exotic microbe or something of that sort. So, and then there's a word of caution that I want to introduce here, that we're academics, many of us, and this is something for you to bear in mind. Academics don't always play well together. They are trained to be independent, they're trained to be critical of others, they're trained to keep their cards close, publish their papers. So the kind of thing we're talking about is a very different approach to studying a globally significant system. And I want to warn all of us that if we don't do this well, it could be a little bit like herding cats. And I think you all know the metaphor of herding cats, but I don't know how many of you have watched the Super Bowl 15 years ago and seen what it's like to actually herd cats. Have you? Some of you have seen this.
This man right here is my great-grandfather. He's the first cat herder in our family. Herding cats. Don't let anybody tell you it's easy.
Anybody can herd cattle. Holding together 10,000 half-wild short hairs, well, that's another thing altogether.
Being a cat herder is probably about the toughest thing I think I've ever done.
I got this one this morning, right here, and if you look at his face, it's just ripped to shreds, you know?
You see the movies, you hear the stories. I'm living a dream. Not everyone can do what we do.
I wouldn't do nothing else.
It ain't an easy job, but when you bring a herd into town and you ain't lost to one of them, ain't a feeling like in the world.
So we're virtually done here. Let me just make one or two final comments. And another comment is very straightforward, and it also involves this little unit. This is what classrooms of today and maybe tomorrow will look like. We'll have live video and other information streaming from the seafloor directly into the labs. And you will think that you're right there on the seafloor. But in fact, we will have the potential of actually delivering it to your pocket all over the world. So hundreds of millions of these kinds of capabilities will be places where you can log in and see what's actually happening in your favorite place in the ocean basins. And you can inquire what's actually happening. It's going to be very exciting. So this is the basic goal. Real-time interaction with the oceans from anywhere on Earth. And I had something special in here for Daniel. And I wanted to show what the full potential is. This is the first successful transatlantic cable. First one was about 1860-ish. This is what we do today. It's incredibly sophisticated what they do. It's beyond belief what they do. And these are what today's submarine cables actually look like. And this is a fiber. You're looking at a cross-section of a fiber there. And they're now putting semiconductor wires down the axis of these fiber, which is fundamentally changing what you can do with the fiber itself. It becomes a sensor. At the cutting edge, we're right at the cutting edge, and we can use this to study planetary oceans. And here's the coverage that's there, and these cables routinely get replaced about every 15 years. So if we look out 30 years, we could all be involved in replacing the commercial cables with cables that are not just commercial, but are also sensing devices. And look at the kind of coverage you could imagine. Look at where we could go if we had the will and the ability to work with industry. For example, there is a group that's contacted us and wants to know how to go from Barrow, Alaska to the southern part of Alaska Kodiak with a cable that both communicates and does science, which is a rare bird right now. But look at this. Here's the kind of coverage that's currently there. What if every part of this could somehow have sensors that are built into the process that could begin looking in new and different ways simultaneously? Talk about a flood of information. Talk about the capacity to identify what the condition of the ocean is. It would be astonishing. So we believe working with commercial outfits over the next 20 years. We've been contacted by 3 in the last 2 years. I've been to 14 different countries in the last 4.5 years. Every single one of them wants to get into this business. And it's a huge, huge opportunity. So I'll leave it with that, and I can sense that you're interested in moving on.
And some others backed up with thank you. Well, I'm sure you have lots of questions and comments. Unfortunately, we have the next sessions beginning, so we're going to break right now, but John will be around, and I'm sure delighted to talk to you. And again, I thank you for a spectacular talk.